Now I explain group. If you see, you know why I explain binary operation, binary map. Group is a tuple, and one is a G, called just set. The other is, I write some big dot. It is called group operation, but it is just a map. So you have a binary map. Now you know this one, and it is a map, but it has a Cartesian product. So binary map. So you have some element G1, G2 from each, but it is same. Then it becomes G1, G2. Oh, it is different from the notation before. One thing I didn't explain was that you usually use this is correct notation, like phi G1, G2. But you know, sorry, it is phi, I write phi. But for the binary operation, you have very similar thing. One is plus or minus times, something like this. So you have A plus B equals something, but it is in fact plus A comma B. But you don't write this because binary operation, you know, two element should be entered. So it is customary, just our habit, to write G1 first element dot G2 instead of dot G1 comma G2. But there's no difference. It is just some habit, and it is more easier to write. And okay, what is group? If this group, this binary operation, this guy, satisfies the axiom called the group axiom, it is called the group. Group axiom is 4. First is closer. Sometimes some people choose 3, some people choose 4. Let me write first what is it. Closer, and it should be associative, and it should be have some neutral element. Some people use identity, but because I love Frederick Schiller's lecture, I follow his notation. And final is inverse element should be exist. So this 4, some people do not include closure. Closure is just in the definition. So if for all element, this means 4 element, every element from G1 and G2 is element of G, then we assume this. Then G1 times G2. G1 operated with G2 is also element of G. So it is in fact just already included in the definition. But because someone wants to emphasize this, people say it is closure axiom. The other is associative. It is just simple. If you do group axiom, group operation multiple times, G3, if you have a G1 times G2, it is another element in G. So this can be also done with this, and this should be same. G1 acted on G2, G3. Yeah, this is associative law. And also, now every group element has some neutral element or identity element. I write E, so it is for or I forget to write for, but I assume I say it is already in there. So for every element in G, there is it means there is something. There is element in G, also it should be element in G, which satisfies G ecton E or E ecton G is just G. This is called, this E is called neutral element. So again, this E is called neutral element or identity element. And finally, inverse element is for all G, of course there is inverse element also. It should be in G, which satisfies G times G1 G inverse, or G inverse G equals identity element. So you get the identity element when you act G inverse. So this is sometimes called right inverse and left inverse, but I will not distinguish. So this is what you call inverse element. So when it acts on some group element, it should give just neutral element. If one thing satisfies, if you have this set and it is some operation like plus satisfying these rules, you call it group. Of course there are many things to talk about group, but I will not go detail because I want to focus on vector space, and I already give this is some rehearsal and I already make some recording for this. Next is ring. If you know group, if we can define, if in fact you don't need to know group, but I want to define group. Ring is similar. Ring is, but in this case triple. So plus and dot. Similarly, plus dot. So R is again a set, and plus R plus is plus is a binary operation. R times R to R, and that is also binary operation with the same domain. Then what is the difference is that if R plus is you also don't know what is, but I'll explain. Abelian group. So it is a group, so it should satisfy 4 axioms, but you have one more additional one, it is abelian. Abelian is simple. If you see this group operation axioms, there is one thing missing different from plus. You know A plus B equals B plus A in many operations, but in group axiom it is not assumed. In fact, it is very special case, so if it is true, it is called abelian group. And another thing is that when you see only R and just operation, it should be monoid. You don't know the monoid, but don't worry, it is just for the group axiom, there are too many, 4 axioms, so you can choose only small number of it. If you choose only closure and associative, nothing else, there should it shouldn't be contain some inverse. It shouldn't, I say, it may not have inverse, it may not have neutral element. What you force is only the operation has some satisfies associative law. This is what we call monoid. Simple example, there is very simple example of monoid. For example, you let us say some integer. It is some notation for integer. So you have this, and this is just this is just some number multiplication. So you know, sometimes 1 times 3 is 3, 2 times 3 is 6, something like this. But this has a neutral element. Okay, let me 1 is neutral element, but there is no inverse because 1 over 3 is not integer. Easy. Yeah. Okay, then other thing. I have to think other thing. Let me write natural number. Let me write some positive integer z plus, and then let us think about plus. In this case, you have let me explain. Z plus is just 1, 2, to infinity. You know, the identity element, neutral element for plus is 0. So, but there is no 0 in Z plus. And even you need minus to tell the inverse. So that is not Z plus. And also minus something, for example, minus 1 is also not in Z plus. So this is some example for monoid. Let us go back. So you have this special case. And then also you have 3 different notation. So you have now 3 R and plus and operation. Now you learn what is the relation between R and plus and what is the relation between R and dot. But you have also relation between plus and dot. So we call dot and plus are distributive. More correctly, dot is distributive over plus. What this means is that very simple. No, I'll not say very simple. I'll say you are familiar with. So A plus B dot C. Let us say A, B, C are element of R. Then A plus B dot C is A dot C plus B dot C. What you are familiar. Also, same for opposite direction. A dot B plus C equals A dot B plus A dot C. This is what you call distributive. So now we have, again, ring is a triple. And the Rn plus, their relation is abelian group. Rn dot, their relation is monoid. And plus and dot, their relation is distributive. We call it is a ring. And for very special case, we don't talk anything about monoid, this dot operation, because abelian group is very, very strong condition. If we force this monoid has more property, we give some special name on it. For example, if you have some, this dot is commutative.